Hello, this is the course for microcontrollers, assembly programming languages, and machine-oriented programming, if you will. And today is the last lecture, so today's topic is going to be about systems on chip, essentially having a whole computer on one single tiny chip, and what it takes to program those, what kind of additional resources these systems have. And how to go about it, what kind of documentation can we read, and how do we read what's included in that documentation. So we're going to talk about data sheets, meaning the documentation, and then we're going to talk about different aspects of systems of chip as listed here. All right, so you may have heard about Arduino, right? And we actually tried to program Arduino a couple of lectures ago. At least I have a recording for that. Maybe not in your version of the course, but I can certainly share a link to the video where I show how to do Arduino programming later on. But the idea is that the Arduino is a platform that has a little microcontroller on it. It looks something like this. They have fancy pictures, but in any case, I think this is more of the original version of the Arduino, and this is the kind of tiny version of the Arduino. The more modern. It's been around for a number of years already. What it has the microcontroller, as you can see here. I'm gonna open the image in new tab so that we can see a little bit better. And so we can connect the Arduino computer, if you will, or a module to the big computer using USB, and we can send programs to it using the same link, the USB. It has the microcontroller. In this case, it's made by Atmel, so it's Atmega 328P microcontroller. And we're going to look into that microcontroller today because that is a system on chip. Basically, what it means, it has a processor on it. It has memory. In fact, it has two kinds of memories. One is the program memory, which is like zip or like flash memory that you can program once and then it retains it even if the power is turned off. And also the random access memory. Besides that, it has a number of peripherals, including analog to digital converter, so that we can attach all kinds of sensors to it. For example, we can attach a microphone to it through a little amplifier. Through these A0 till A5 pins. So all in all, we have 6 analog ports that we can hook up to this controller, right? And then we can have digital pins. We can attach things like switches or LEDs, or manage some more complex devices such as motor controllers. For example, we could have a little robot that is driven by this Arduino through a motor shield. So there are a number of other devices that are called shields that you can attach to Arduino through these pins. Basically, you take another board, you sort of slap it on top of this one, and that's how you can get different functionality out of this board. And so I'm looking if I have any Arduino in my proximity here. So I believe here is one, if I can get it out. Well, I got out this one, right? So I'm gonna show you. So this is pretty much the same board, right? This is how it looks like in comparison to the size of my arm, anyway. And another thing is that there are different versions, in fact, of this Arduino. As the year went by, people introduced different kinds of controllers, different kinds of form factors The smaller ones, let's look at hardware page, for example. And here you can see that there's this classic Arduino Uno. Then there's Arduino Leonardo or a few other versions that can pretend to be a keyboard, for example. You could write a little program that acts as a, you can create a hotkey sort of controller where you have keys that you can just push, and then the Arduino would send certain keystrokes, for example, to turn on the music or to do something else on your computer. All right. And then there are Arduino Micro or even Arduino Nano with a smaller size than the other ones, and then a few others, right? Then there are Arduinos that have other peripherals included, such as Bluetooth or some sensors. For example, this one BLE for Bluetooth and Sense, and eventually even the Wi-Fi here. Eventually the Arduino board got improved in a way that the microcontroller that is on the Arduino, on the classical Arduino, on this one, is actually not that powerful. It has, a few kilobytes of RAM. Not the megabytes, not the gigabytes, but kilobytes. And it runs at a few megahertz, not gigahertz, right? So maybe 4 megahertz is what it runs at, the speed. But eventually people wanted to create more complicated projects that would require faster processing speeds. So people introduced new versions of Arduinos that were based on ARM processor, for example. And there's even beyond those, you can have a lot of all kinds of Arduinos here. You can have the prototyping boards. You can have boards to which you can attach all kinds of sensors or switches or lights or peripherals. Here's a board with 4 relays, so you could attach even the bigger devices to it, so it can manage lighting in the room, for example, and things like that. Right? So many families. So what Arduino really is, it's a platform. So it's not just a hardware, but it's a platform because it has all kinds of hardware implementations for the devices. But it also has the software that currently is at version 1.8.18 for any of the platforms, the popular ones anyway, such as the Windows, Linux, or Mac OS, so that anyone can actually start programming using Arduinos. And many people do. Some do it for education, some for fun, some create all kinds of arts projects and so on. But in any case, at the center of it, let me go back to this picture, is a microcontroller, which is a system on chip. So today I'm going to look at the datasheet for this microcontroller at Mega 328P. You can vaguely read the writing on this one. Right. So maybe on mine we could do it a bit better, but I guess not. So, never mind. And I have this datasheet open already here. All right. So what this is the documentation for a chip. And in electronics, usually when you when a business creates and sells a chip, it comes with documentation. So it comes what's called a datasheet, and this datasheet describes this device from hardware aspects and sometimes also from the software aspects. Besides datasheets that are like the specification page or documentation, there also happen to be application notes, ANs, and those talk about how to use that device in different contexts. How to apply device, for example, how to take a microprocessor and how to make an EKG, electrocardiogram device out of it, or how to make a chip and create a walkie-talkie out of it, or things like that, or how to use certain aspect of a chip, such as the serial port, right? But the datasheet is the very basic documentation that we usually take and look at when we have to work with a particular device, be it a system on chip or a processor or a memory chip or whatever else. All right, so let's see. Let's take a look at this datasheet and what kind of sections does it have, right? So usually at the beginning there's a section about features. Usually it's a one-pager. In this case, it spans actually 2 pages that lists the key parameters of that device. And often it describes a family of devices. So you can see there are actually several devices described here. Atmega 48, 88, 168, 328, which is the one that's used on Arduinos, right? So all of these devices share these specs, these specifications, these parameters, but they may differ in terms of how much memory, for example, they have. So in this case, we can see that random access memory, the static random access memory, SRAM, is 512 bytes, only bytes, for the Atmega 48 device. So it's a smaller device, it's a cheaper device, simpler device. It hopefully also consumes less power, right? So it's not that always we need very powerful, very fast devices. Sometimes we need a small, tiny device that will drive the cost of the whole application lower down, and that will also last longer on the same set of batteries or on the same set of charge for low power applications. All right, so it's not always that more memory is better, right? But in any case, if you want a lot of memory, so for 1K, a lot of memory, in comparison to desktop computers, this is like nothing. But the bigger device, that's what it has, 328, right? Also, in terms of the flash memory, flash program memory, that can be used to store the programs, the binary code, we can have up to 32 kilobytes. So it's interesting to notice that the program memory is way larger than the data memory. That's where the emphasis is for these devices. And then there are other parameters. For example, how many times can we reprogram this device, right? So we can reprogram this device 10,000 times, which seems to be a lot on one hand. On the other hand, if you have a program that's actually trying to rewrite electrically erasable PROM, so that's another part of the device where it can serve as a memory that's retaining the data even if the device is off. So that one can be reprogrammed way more times, 100,000 times. But if you're using a variable and if you're changing its value 10 times a second, then this is gonna last you about 10,000 seconds, which is not that much actually, if you convert that to hours. A few hundred hours basically is what it is, I think. So you have to be careful when you write programs for these devices. Where do you write data? How often do you write that data? It's okay to use SRAM memory for frequent updates, but if you're using EEPROM, that should be considered like a hard drive, where you write once and then maybe read it many times, but you don't write it too often. Okay. What else? There are other features. Let's look at the peripherals. So peripherals are devices that are built into this chip. So for example, it has timers counters, which is a device for which you can set up, okay, please count 100 and let's say please count 1000 times, where every time you count is going to be 1 millisecond. So for each millisecond, add 1 to the timer, and when you hit 1000, then please fire an alarm. So that kind of device. It's like an alarm, basically. It may have several modes. It may have one-shot alarm, where it's going to ring only once, or it may have repetitive mode, where it's going to ring every once in a while, depending on how often do you want it to create an interrupt. So that way you can use it for your programs. And apparently there are 2 of these timers. One is 8-bit, meaning that it can only count up to 256. So that's not too far away. And then you have a 16-bit timer, which is a bit finer resolution, and well, we can use it as such. Let's look at what else do we have. We have the pulse width modulation channels. That's what PWM stands for. What this is basically where you can shape a pulse that's being sent by, you can send a high for a certain amount of time, and then you can send the low for another amount of time, and then you repeat, right? So it's like sending 1 for some time and then sending 0 for some time, and then you repeat. And based on how long this one period is, you can do different things. For example, if you attach a motor, of course, you would have to attach it through a certain device, because the chip itself cannot drive a motor. But if you have a motor controller and then you attach it through the PWM, then you can change how fast the motor is running, or you can change how much power does it have. If you attach a little LED, you can change how bright the LED is, for example. If you attach a speaker, then you can actually play different kinds of sounds at pseudo volumes, different volumes to that sound. And many other applications. Certain sensors need this PWM shaped in a certain way. For example, the dust sensor. The way a dust sensor works, for example, it shoots a laser, and then the laser reflects from some dust particles in the air, and those reflections hit another sensor, right? So this laser pulse also has to be shaped in certain ways so that we can actually correlate the number of dust particles in the air to whatever the sensor is reading. Right? Okay, so let's look at what else do we have. We have what's called the US ARTS. Universal Serial Asynchronous Receive Transmit, or Receiver Transmitter. Right? So basically it's a serial port. It's a device that allows communication from this chip to outside using just 2 wires, receive and transmit. Right? And there are some other ways for the communication. For example, there is this Serial Peripheral Interface, SPI, serial interface, which is using 4 wires. One is for the clock, so it's a synchronous, and one is for data that is going out. One is for data that's coming in, and then one is for the selection of the device that you want to talk to. Right? And then a few other popular interfaces, such as the 2-wire serial interface, also sometimes called the I2C interface, even though there might be some nuances, some differences there. And something else. All right. So this is a list of features. What's also pretty important is, for example, at what voltages can we use this chip? Right? Can we use it just at a small 3-volt battery, or do we really have to have 5 volts or something like that? and other application specific parameters. So for example, there's a temperature range. So if we want to use our smart device somewhere outside, then we have to consider how cold or how hot can it become before it becomes unstable, right? So this doesn't seem to be a concern in a typical environment where people live. But if you want something extreme, let's say if you want to go to Antarctica where you could hit minus 50 degrees, or even create, I don't know, something for satellites, then you have to think twice if you're gonna use this chip, or you need to look for a different one. And there is description about the speed as well. So you could see that it can run up to 4 megahertz. Again, it doesn't seem to be a lot. And in fact, it turns out that it can run up to 4 megahertz if we're using low voltage, which is good if we want to have a low voltage application. But what if we need to run it faster? So it turns out it supports up to 20 megahertz. But in that case, our power has to be at least 4.5 volts. So probably at 5 volts. We cannot do it at low voltage, right? So these are, the topics that we could discuss at length if this was an electrical engineering class. So I'm not going to dwell too much on those. But at the same time, these are also things that we need to consider when we design for something. And yet another thing is how much power does it consume? And that might be important if you want to, for example, create a wearable device. If you want to create a little arts thing that you can snap to your clothing, and it would play nice, dancing lights or something. Jewelry type of piece, digital jewelry. Then you would have to consider how much power does it consume and how much power does the battery has, and then calculate how long is it gonna last. Now this also seems to be electrical engineering kind of thing, and it is, but you can also influence this with the way you write programs. For example, if your program does a busy wait, if it just loops all the time and tries to do something, that means that you're going to be all the time in the active mode. You're going to consume 0.2 milliamps here, right? But this chip also has a mode when you can put it to sleep, in a way, sort of power down mode, right? So if you could write a program that does something useful and then it goes to sleep for a while, and then it wakes up and does something useful again and goes to sleep again, and so on. It's something, sometimes it's called a duty cycling. Then you could actually save a lot of power. So we can see that for the complete power down mode, it goes down to 0.1 microamps. So that's about 2,000 times less than the active mode in terms of power consumption, right? Except in power down mode, it's really doing nothing. Let's say if you want to keep counting time while power down, if you want the clock to be still running, then you're gonna want to use perhaps RTC, real-time clock device, right? And in that case, the power is going to be a little bit higher, right? So it's going to be 0.75 microamps, which is still, about the about 100 times or even more less than in active mode. So it's worth thinking of how to write those programs, how to design those systems so that you can maximize the sleep time and minimize the actually active time. And then you have to think about your applications in your programs. How often do you have to go to sleep? How often do you have to wake up? At what times? How do you, let's say, if you have a network of wirelessly connected nodes, how do you manage the communication protocol in your software so that when all of them wake up, they are synchronized? so that it's not the case when one wakes up and then goes to sleep, then the other wakes up and hears nobody, goes to sleep, and then this guy hears nobody, and there's no communication going on between these guys. So how do you make sure that they all go to sleep for a while, but then they wake up, and then they maybe wait for the other guy to wake up, and then they can talk, and then they go to sleep again? How to do the time synchronization, things like that. All right. So there are a lot of issues on software development, and even in medium to even high level of abstraction of software development, that you can use if you take in account these power consumptions while designing for low power. All right. If there are questions, please do ask them or write them in chat, and I'll try to address. All right, so for the rest of the document, of course, there's this table of contents, but the typical chapters we can sort of scroll. Well, you see the document is 600 pages. So another note to take is, to keep in mind, is that we're not expected to know this by heart or to read it line by line when we are using, but we need to know of the certain chapters that may be important to us, and then we can focus on those depending on what we're doing with this device. All right, so what we probably want to talk about is about the CPU core, so that we know what kind of processor does it have, and also about the memory, so that we know what kind of memory map does it have, where are the important sections of the memory, what are the addresses for certain, I don't know, registers or interrupt vectors or things like that. The things that we are going to use in our software, right? Then there is the section about system clock and clock options, which is more towards the person who is going to do the electrical design that's using this chip. But it may also have a digitally configurable clock, which could be configured or calibrated using software. Because these devices, they are made to be as cheap as possible. So therefore, their internal oscillator may not be as precise. So it may be sometimes faster, sometimes slower. But if you're doing a serial communication, then it's very important for you to have a very stable clock and very precise clock on both ends of the communication, of course, right? So for that, you sometimes have to do the calibration of the hardware in software, right? And that you can use with what's called the external oscillator or external crystal. So if you're doing something like that for an operating system, for example, then you would have to read through this section and see how these things work. Now, we did talk about the power management a little bit, and different kind. And at least we talked about 3 modes. One was the active mode, when the processor is just running at full blast, at full speed, and doing everything that has to be done, everything that the program tells. And then there can be several sleep modes, or power down modes, or standby modes. Each of those differ by how much power does it consume, and that is in turn based on what other resources is it taking, what other things is it doing. Is it counting the clock? Because everything takes some energy. If it's counting the clock, then it needs some energy for that. What if it's does it have to store and keep the memory content? If the memory is powered, the static memory, and if we need to remember all that, that will take a little bit of power, but it will still take that power, right? And depending on, maybe there are some other things that it may do. Is it open for interrupts, the external interrupts? Maybe we want to put this processor to sleep until something happens, outside, until maybe someone pushes a button, or until maybe someone takes it up and shakes it, right? So just as with the smartphone could go to sleep until there's a call coming in. So maybe it's going to listen for the interrupt that's coming from the radio chip. And things like that. So that's why we have different kinds of power or sleep modes for devices. Now, there is a section about the, what happens when we push the reset button, if you will, right? So except there are no buttons on the chip, there are signals that we can raise or lower. So what happens, or how do you reset the system? And also what happens when you reset the system. That's what the chapter is about. There's worth talking about the Watchdog. So Watchdog is a device that kind of monitors whether our processor, whether our system is running fine. What if we are stuck in an infinite loop, right? These devices, the way we program these devices, they are meant to run forever. So if it's stuck in an infinite loop, then it's stuck in an infinite loop forever, which is not a good thing, right? So therefore, we may have the device on the side, what's called a watchdog, that checks once in a while, okay, is everything fine? So the way it works is, it's like a timer. So you set that timer to some big enough value, and then the timer just counts down. If you let it count down to 0, then it resets. Then it resets the whole chip, assuming that something went wrong and we need to restart the whole system. All right? So therefore, if everything is fine, then you have to, set this watchdog timer again and again so that it does not get to count down all the time. So you have to kind of update it once in a while. So that's what a watchdog is. And one of the classical mistakes for beginners working with systems like that is when people don't know or forget about the watchdog timer. So you write a program, you run it, it runs for a little bit, and then it resets. And you're thinking, why? What happened? So it turns out the watchdog timer is thinking that, it's time to reset, and you just didn't think about it. All right. Now the next section is about the interrupts. So the system on chip, it can work on itself. It can, do computations, solve the problems, but it's really meant to work with the outside world. It is meant to be event driven from the outside world. And these events can be of all kinds. It could be just when I, bang on my keyboard. So each keystroke can be an interrupt to that device. And whenever I push a key, the device looks, aha, this key was pressed, so that means I need to run this function. Things like that. Right? There can be interrupts coming from other devices, from the network connection. For example, hey, there's a new data packet for you. You need to, process that data pack. Or, hey, the battery is going low. We need to do something about it. Right? Maybe we need to, power down or turn on the low battery signal or something else. Okay, so this section talks about what kind of interrupts can we have, external interrupts coming from outside. It also may have internal interrupts. So some of them may come from the timer. Remember, we were talking about timers. So when the timer counts until some value, and then it may fire an interrupt. And when that happens, again, we can start a certain function that takes care of that interrupt and so on. The next is about ports, input-output ports. So if you remember the picture that we had earlier, we have these pins, these places where we can attach wires, and we can attach either sensors or buttons or devices through these pins. So those are called input and output ports. They are somehow connected to these pins on the microcontroller down here. Except they are most likely on the other side. The connections are on this side. You can see how this pin goes to here, this pin goes to there, and so on, right? So thanks to those ports, we can connect this processor to the outside world. and it talks about what kind of ports do we have. We may have just general input and output pins, meaning that you can set 1 bit or you can read 1 bit from that pin. Some pins may have other functions. We can reconfigure them to become serial ports, for example, or pulse width modulation outputs, or other functions. So therefore, we can also talk about alternative port functions here. All right. Okay, so then there's this talk about timers. We did talk about those already. There can be several. Then there's the serial SPI interface. I mentioned that as well, just as the universal serial asynchronous receiver transmitter. And there might be a couple of those. So this is marked with 0. So there could be one marked with 1. And then there is ADC, or analog to digital converter. So when we read signals from the real world, from analog electronics, such as from a microphone, the signal is not digital. The signal is usually, it's more or less voltage or more or less current coming from the sensor or from the device. So that needs to be converted to a digital, to numbers basically, so that we can do some computation on them. That's what the ADC device does. That's built in, right? Of course, if you want to use that, you need to know how to actually program it, how to start it, how to know when the read is done, so it's not instantaneous. First you say, I want to read something from ADC, and then after a while you can get an interrupt, for example, or you could get a guaranteed out value after certain time. So these are the kind of things that are described here. And also there's other things that are, again, more towards the electrical engineers. For example, how much noise do these analog signals may have? How precise is the ADC? How many bits can we get from this ADC? There are some other devices such as an analog comparator. So for example, you could set certain analog voltage and compare it to the voltage that's coming in. So you could set threshold, and if the sensor goes above that threshold, then you get an interrupt. But if it's still below, then everything seems to be fine. Then you don't have to worry, for example. That could be an application. For example, that analog signal could come from a temperature sensor. And if the temperature is warm enough, then it's fine. But if it drops down, then you have to turn on the heater, for example. If you are building a smart thermostat for your smart home application. All right, so let's see what else. And then there are a lot of electrical characteristics again about, the voltages and amperages, how much current does the device consume in certain modes of operation, what are the timing parameters, how fast does a device change from 0 to 1 on its output signals, for example, right? So a lot of information here. Let's see if we can actually find something useful. I was hoping that it also has a table of contents, but it doesn't seem so, at least not here. That's all right. We can just, quickly scroll through it and look at pictures, if you will. All right. Okay. So these devices, they may come in different form factors, in different packaging. So the classical one we already saw is in this, what's called a DIP package. It's fairly big. It's fairly bulky in comparison to modern electronics. But it's easy to handle if you are just a beginner, if you want to unplug it and plug a different device in here. When you're a beginner, sometimes things go wrong, so you may burn it or something else may happen. So that's why it's so big and also it's a bit of legacy. Of course, you can see that there are some other devices on this board that are way smaller, way tinier. So these are not the microcontrollers that I'm talking about. They may serve different functions. So this one is most likely, so this one, for example, has to do with the power supply to make it steady. This is the controller for the USB port, and so on. And these are just the resistors, I think. It's not even chip. How tiny things can be. But turns out, even this device, it may get packaged in a big package and also in a small and tiny package. In comparison, on the left you can see the old big one. On the right you can see the tiny one. So once again, it serves the same function more or less, but it is much smaller. Maybe you need a smaller application here. All right. And even on the big devices, you may have, let's see, do I really have only the tiny ones? Yeah, unfortunately. So what I see here the controller, the same controller is this tiny thing here, right? As opposed to the big one here. Moral of the story, the same device may come in different shapes while doing the same functionality. Right? So once again, this is important for those who are designing these boards. Well, like these boards, thinking of, okay, where should we place the chip? How should we connect it to other chips and things like that. For the programmer, it's not so important. It may become important if you need to know which sensor is connected to which pin here, so that you know from the program how to program the device to read from that particular pin. All right, let's move on. Let's check it out. So it has the pins described, and the pins may have the GND usually is the ground, and A ref is the voltage reference, for example. A VCC is the power voltage, and things like that. That VCC is a power voltage for the digital world. A VCC is for the analog world. Things like that. Once again, the electrical engineers may read. But PC0 actually means that this is port C, pin 0. So this may become important to you if you are programming that device, if you're writing programs for that device, so that you know which pin, which port should you read. And then there's some additional information. So these pins can serve different functionality. On one hand, maybe it can be just a general purpose input-output connected to a push button or a little LED, or it could be a serial port, or it could serve as an interrupt source. Like in this case, there's interrupt 9 and interrupt 8. We can barely see, but if we zoom in, I guess we can see much better, right? And so on. All right. Okay, so we've seen enough of this picture. Then there is a lot of description about that. Now, this is a block diagram of the actual system on chip. Let's dwell on this one for a little bit. Okay. So this whole thing is a chip. This whole thing is what you can see in this black device. Right. So it has the processor. So CPU is here, and that's what we are programming. It has the flash memory, which is where the program is going to go. And it has the static RAM, which is where the variables are going to go of our program, most likely. There is another kind of memory, what's called the EEPROM, electrically erasable, programmable read-only memory, or persistent read-only memory, right? So this is sort of like where we could write the configuration for this device. That will be remembered even if we turn it off, right? Or maybe there are some parameters that we want to retain, maybe calibration data for this device, maybe some addressing, or something else that needs to be remembered. So in fact, it has 3 kinds of memory, which is kind of interesting. Now, what else does it have? You can see that there is this Watchdog Timer that I was talking about, and the Watchdog Oscillator. Basically, it's like a clock that's sending, that counts that Watchdog Timer forward. And when the Watchdog Timer has counted far enough, then it sends a signal to the power supervision device. So that device, among other things, is taking care of the smooth and solid power for the whole system, but also it's taking care of the reset. So when you just power it on, it needs to reset the whole system. Or when the Watchdog Timer fires, you also will reset. Okay? So POR means power on reset. Right? It may also check for brownouts. For example, what if the power is not stable enough, but what if it like lowers for sometimes, or what if it spikes? Then we also may not sustain a stable, performance of this device. So the power supervision unit may look for that, and if the power goes way too low, it will reset device or power down the device, or create an interrupt, so that the software can feel that, hey, the power is going down, the batteries are going low, so maybe it's time for us to go to sleep, or at least to send the one last message, hey, come and change my batteries, something like that, right? Okay. So let's look at the bottom here. We can see there are a bunch of lines going out of this device towards the bottom. And these lines are attached to the ports D, B, and C in this case. But there are other ports as well, such as A, except where is it? How come I don't see it? But it must be somewhere here. That would be weird if they started from B rather than from A. In any case, so these are the ports that provide the interface to the rest of the world for us. All right? And these ports can be configured as general purpose input-output ports, driving the LEDs or simple things, or they can be connected to other devices, as we can see through these lines that go up here, for example, to the analog comparator here. Or from this port C, we have a line going to the power supervision, or a debugging by wire. So it turns out we can debug the whole device remotely. We can see that the reset signal also comes in here through this port. Let's look at the analog to digital converter, A to D converter. So apparently to this one, we also come from port C. Right? So the ports are what connects the system on chip to the rest of the world, to the outside, and that also connects to all kinds of peripherals. Now, let's look at these big fat arrows here. So this is called a data bus. So this is the bus that allows the processor to communicate with all kinds of devices in here. Right? For example, it can communicate with the serial port, with the SPIs, with a 2-wire interface, with the timers and counters of different kinds, with the analog to digital converter, and so on, and even to the EEPROM. The way this communication is organized, usually in microcontrollers, that these devices have registers within them, And depending on what you write in those registers is going to drive how this device is, what is it doing, right? How is it doing that? For example, you could set the baud rate for the USART. You can turn out various modes for these controllers. You can turn on whether you need a parity bit or you don't need a parity bit, right? If you want to learn about, how to configure this device, you're going to learn about which registers do you need to change for it to do this or that thing. And these registers will appear as locations in memory to that processor. So it's going to be as simple for your program to write a certain address in the memory, so it will be written to that register. In some cases, there are special assembly commands for writing to those devices, to those registers. But in many cases, they are all memory mapped, so we can access them directly. All right, so let's see what else is there of importance. So sometimes you get the comparison tables, and these are the different devices that are described in this datasheet. For example, the Atmega 328P is the one that we may have on our Arduinos. So it's this black thing once again. And we can see that the flash ROM is 32 kilobytes. The EEPROM is 1 kilobyte. So that's quite a bit of memory actually. But that's the one that we can write and read only 100,000 times. And then there is this RAM, random access memory, that's 2 kilobytes. That's for general purpose variables and things like that, right? Okay, so if we look at the processor itself, then the way the processor is set up, it talks through the 8-bit data bus. So it turns out it's an 8-bit processor, right? And we can also see that from here, that it's 32 registers. Each register is 8 bits, right? So even the size of the registers is smaller than for typical processors. It's not 32, it's not 64 or even 128 as modern processors have. It's just a different class of device. And this is basically the architecture, how it's set up. We have the arithmetic logic unit. It can read from 2 registers. It can write it to the data bus, and from data bus it can write back to the registers, or it can write to any of those devices that we just discussed earlier. Right. Then there is this program counter register, which points to the current instruction, just as we discussed in our class when we were doing the assembly programming for ARM processors. And the memory for program is the flash program memory, right? So this architecture is different in a way that the program sits in one memory and the data sits in random access memory. The data is RAM here, right? Or EEPROM as well. All right, so as the program counter counts ahead, we can read instructions one by one. They're gonna get decoded, and these decoded control lines will be connected to the rest of the system and to drive what should be done. For example, which register should we read into ALU, where should we write back the result, and things like that, right? So that's about the CPU. Now, as mentioned earlier, pretty much all the devices within the system on chip are driven by special purpose registers. There may be a lot of them. There may be a few hundreds or even 1,000 of those registers, depending on the device that we're talking about, right? And each of them are described somewhere in this document. So for example, if we look at the SREG, which is AVR, AVR stands for this processor, status register, this register actually contains several bits, Remember, there was this ARM processor had a status register, and there were 4 bits that we cared about. That was the carry, negative, 0, things like that, right? Overflow was the last one. And look at that. This register for the AVR has a similar set of flags. For example, there is V is the 2's complement overflow flag. S is the sign bit. There's half carry flag, which is not quite carry. And then there's carry flag and the 0 flag. So, and the negative flag, right? So these are very similar. These last 4 are just like we had in the ARM processor. But there are some other flags. For example, there's one flag that says whether the global interrupts are enabled or not. Meaning, are we going to hear if anyone sends an interrupt to us from outside or not? Okay. Okay. This processor has general purpose registers, just as any processor have. In our case, we have 32 of those. And, well, these are the addresses for them. So as I said earlier, you can actually access registers by the address in the memory in this architecture anyway. And then if we look at some other registers, for example, there's stack pointer, high and low register as a separate register. But I'm gonna go down eventually to look at some other registers and how they drive the functionality of the system. We can see the assembly code or C code as an example for this device. And what we can see in these kind of programs quite often are the names for these registers. And there is usually a fairly long list of registers. There's a file, include file, that defines these names. And we are using them here, like EECR or EEMPE and things like that. So these names we can use both in the assembly program or in the C program. Okay. So in this case, what we're looking at store byte information. That's what I think this instruction was, if I remember. But we also have out instruction, and the out instruction is writing to SREG, to a certain register, and it's writing the value from the general purpose register to this register. All right. But we could write the whole thing in the C programming language as well, and the C compiler for Atmega, for Atmel processors, is gonna understand where those lines actually mean the specific either registers or constants, things like that. All right, so memory map. If we look at the memory and how it's mapped, we can see that there is an area from 0 to 7FF, which is applications flash section. So this is where the program memory is going to go. Right? But at the bottom, we have a special section for the boot flash section. So this is similar to a BIOS ROM on desktop computers. So basically what you're going to have a small program sitting there that will be run every time you reset this system. And once you reset it, then you can decide whether you want to put this system into a programming mode or some other mode, or start a certain program from the application flash section. All right. And here's the table that tells us what memory area is for what purpose, right? So there is internal SRAM. So apparently the memory, random access memory, starts only from this address 100 and goes on to whatever size the actual chip has. But the very first addresses are for the registers, as in this case, or 64 input-output registers. So those are the registers that are driving certain functionality of the system on chip, and even more registers that are driving the external functionality of this one. Right? So that's what's interesting, is that these registers actually get access through the memory addresses rather than with a special command. All right. Okay, so let's look at what else do we have. So there are timing diagrams about how to access memory, for example. But once again, this is probably more interesting to the electrical engineering. And then you have a list of different registers and the functionality that they control. So let's try to find something that kind of makes sense from a practical application perspective. So this picture is about how the clock is being driven, how the clock is being configured. So it turns out you can use things like clock multiplier to actually change how fast the actual clock runs for your system. Right. So remember I was talking about clock multiplexer, not the multiplier. So you can choose whether you run the system from internal clock or from external clock or from the crystal oscillator. So you can attach a crystal to this chip, and most likely it has it somewhere. Yeah, right here. That's a little device. It's called a crystal here. So that will provide a stable clock of probably 32 kilohertz to this system, and you can use that clock to actually configure the internal clock that runs at much higher frequencies to calibrate it. All right. So what I wanted to go to, I wanted to check out the actual registers. Let's see if we can find something relevant to timers, perhaps. System control on reset. Okay, let's go to the table of contents at the beginning here and take it from here. So let's say we want to go to I/O ports. Let's look at the I/O ports. So each pin that's connected to the outside, it's electrostatic discharge protected, so that you don't zap the chip just by touching it with your finger. But what's interesting is that there is this pull-up resistor that you can turn on or off from the software. If you're reading from that pin, and if nothing is connected to it, then maybe you want it to read as 1. So that's what the pull-up is. You could have a little switch, a button attached to it, and whenever you push that button, then you get the 0 on that pin. But what if it's not pushed? Then you should have a stable 1 on that pin. So that's what this pull-up resistor is for. And then there are schematics about how to deal with them, but there's also a code how to actually program them. So when we work with the input-output pins, we need to probably define whether we are going to use the pull-up resistors or not. And we do that from software, right? So we are loading that value. We're going to prepare that value in the register 16. And we're going to set the certain bits that will define those pull-ups. And we're also going to define the directions for the pins of that port, whether they're going in or out, whether we're reading them or whether we are going to write those pins. All right. So as we are setting those on two registers, register 16 and 17, the values have been calculated. We can write these values to those special registers, port B and DDR B, right? DDR probably stands for digital data read byte or something like that. And then what's interesting is we are attaching another instruction that does nothing. So it turns out we need to wait for one clock cycle before these things take action. And only after that we can do something with these pins. So we can, for example, read the pins from the port B. Right? So how do we know which pins to set and which pins to clear, depending on the functionality that we want to get out? Then we need to get to the section that describes those registers, right? So for example, port B or DDR, data direction B. Let's see if we can find them here. And there we go. So there is a table describing different kinds of functions for these ports. And I'm looking through this, and I think that information is encoded in these tables. Right. Anyway, so we are down to the register description here. And here's the port B register, for example, right? So every register has a certain number of bits. In this case, we are using all 8 bits. And these bits have certain values, so port B7, port B6, port B5. So you can sort of access them by this reference. So SBI instruction that I looked earlier, it's not the store byte, but it's rather set bit. And then we can use these values to determine which bit do we want to set or read. It also shows for each bit separately whether we can read and write this bit, because there can be bits that we can only read, such as in this case, for this MCU control register. We can only read this register, and these bits actually are not set to anything. They are sort of reserved. But there can be other bits that you can read that have actually meaning, but you cannot write. Okay. So indeed, the first port that we're dealing with is port B. So port A is not here for some reason. Data direction register, or R is for register. Data direction register for the B port. Once again, we have 8 bits, and for each bit we can specify whether that bit is going to be read or written. And each of those bits in reality is actually not these bits, but the ports of the bits of the port B are connected to one of those pins on the physical controller. So by configuring these registers, we are deciding whether we're going to read this pin or write. Right? And then in this port B data register, we're, I guess, deciding whether there is going to be a pull up or not. Right? So let's see what else we have here. We have the bit 4, which is the PUD register, read write. Pull up disable. So when this bit is written to 1, the pull ups in the I/O ports are disabled even if certain bits are configured to enable pull-ups. Right? So this is like the pull-up override bit. And this could be used if you want to sort of disable all the pull-ups for the whole chip. And why would you do that? For each pull-up consumes certain amount of energy. Let's say you want to save energy even more, then from your program you can disable all the pull-ups, because at that time you're not going to read from those pins. Only when you read from those pins you can enable pull-ups, you do the reading, and then you disable the pull-ups. Right. So once again, what we notice here is that we can manipulate the power consumption from the program if we know the structure of the processor and the features that it provides. Right? But in general, this is how it is. If you want to use, let's say, this or that functionality, you have to read about that functionality, about the general purpose input-output pins, or let's say you are using the USART, you maybe want to configure the serial protocol device. You read about the logic of it, you read about what are the meanings of the signal names, and then you look at the concrete registers and see where those bits and pins are. And then from your program you can set them accordingly, right? As it's shown in some of the examples here. Right? So that is how you program this system and device. This is generally the architecture for a system device. Right? We did talk about different protocols that it may have. The serial, this SPI protocol, I2C. There are some other protocols such as one wire, or CAN protocol is often used in automotive industry for the controllers that are built into your car, for example. And that's how they communicate with each other and also with some other devices. We did talk about peripherals, about the Watchdog Timer. We didn't talk about bootstrapping too much, but essentially I did mention that this device may have a special area in the memory where the actual bootloader is stored. I think it was at the memory section. Right. So we can have boot flash section. And when you start it up, there's this little program that runs first. Or even when you reset, that's what's being started. And then it starts a certain program for some memory in the application flash section. And that's how the program starts. And then we did talk about the Watchdog as well, which is meant for, saving us if something goes wrong with our system. Saving through resetting the whole system and hoping that then the system can pick up whatever it left and keep on running. All right, so I believe that this is all that I planned to talk about today. And I hope that this was somewhat informative, at least, about systems on chips that have, widespread use today in all kinds of devices. You can look around you in your room and you can notice many locations where those devices are being used. It could be a network router, it could be your smartphone, it could be a little wristband or smartwatch that you have, it could be a air quality sensor that I have here. Even our computers, desktop computers, are full with these little controllers taking care of different aspects of them. such as the temperature, whether it's not overheating, such as controlling the fan speed so that the processor is being cooled sufficiently, or the battery charging, and so on. And when you have to program this system on chip, then usually you go through the datasheet, look at its features, look at the specific ways how to actually configure it, and then you write programs and test them. So that's it for today. Thank you all for who are watching this.